So, first step into year 11 chemistry and all of HSC chemistry together. We're a term ahead, which is great, but we'll essentially be making our way through module 1, which is properties of matter. Today's session won't be overly complicated, a lot of very simple concepts. So it's kind of like a warm-up and a way for you to gauge and see what the waters are like before you dive into the harder bits of chemistry. In fact, the whole of module 1, for the most part, is very, very intuitive, very straightforward, just a bit of memory work, and there's not too much in the way of calculations. So would you say you're, in terms of writing responses and calculations, what would you say is your strong suit out of those two?
I think calculating.
Okay, good. You always want, like, if you are a slight bias towards being a little bit better at calculations, that's perfect for chemistry, because it means you won't struggle with the calculation parts and the written responses will come relatively easily just with practice. So our mission for this term, because we're starting so early, our goal is to have all the content done by week 2 of your school term. We'll take 5 sessions to finish the whole module, and most schools take about 8 weeks, but we do it quickly. So 5 weeks, week 2 of your school term, you'll finish the module. We might do a revision session after in week 3. And in week 4 of school term, I'll give you a chemistry exam, your first one ever, which will be a little bit difficult. That's the point. You'll learn a lot from it. And then when you start next year, you'll have all that knowledge from module 1 already ready to go for the first term as we start to work through the next module in that first term. Okay. Any questions on how it's going to work?
No.
All right. Let's get started then. You can think of STEM subjects in chemistry as having 3 stages as you study them of how you learn. You have awareness, understanding, and exam readiness. So when we're in these classes and you're seeing the content for the first time, we're in this stage. We're in the awareness stage. When you go over content for the first time, you can only really expect that you hold about 33% of what you learned the first time. So if you come to this class and you're like, okay, great, I learned everything, that would be the wrong thing to take into the next weeks. You should be coming to these classes and be like, okay, I've covered everything for the first time. I'm about 33% of the way there. Because then the next thing you do is you study what you covered to gain at the understanding stage. And that's where I say you're about 66% of the way there, because you can't get into an exam room without having also done past questions. And that's how you get to exam readiness. So 3 stages. Think about it that way. And we're into assumed knowledge. So in terms of things you sort of should know already, you should know roughly the difference between a solid, a liquid, and a gas. Is that okay?
Yep.
Good. So you would know that solids are arranged in a lattice and they're just vibrating side to side. A liquid is free moving particles within a fixed volume, like in a beaker, for example. You could have liquid sitting at the bottom of particles moving around. And for a gas, it's free moving gas particles, which are free to move in the entire space that they fill up. Which is lowest energy, which is highest energy?
Oh, sorry, I don't understand.
Yeah, which out of solid, liquid, and gas has lowest, next highest, and the highest energy?
Does solid have the lowest?
Yeah, perfect. The solid, they're stuck in a lattice. They can't escape the attractions of each other. Liquid is when they can break free of each other for the first time and move freely. And then not until liquids move fast enough can they then start to bounce around. If you give them more energy, bang, they can start to leave and they become gas if you give them enough energy. So it's all about energy when you're transitioning between states. So how do you go from solid to liquid or liquid to gas? Think about water. How does water turn into a solid or water turn into a gas? What do you have to do?
Mm, do you have to heat it?
Yep, and that would turn it into
A liquid?
sure, yes. So ice going to liquid would
Mm-hmm.
be the application of heat. And how do you go from liquid to gas?
Um, do you evaporate it?
Evaporate it. And how do you evaporate water?
Mm, I'm not sure.
You just apply more heat once
Heat?
again. Yeah. So think about your kettle. If you ever boiled water in a kettle, you're doing
Mhm.
just that. You're taking that liquid water, turning it into gas, and that's essentially what's happening.
Yep.
The crisscross method. Have you come across this before?
Yes.
Okay, great. So MgCl, for example, if you bond it to Cl and make an ionic compound, you can figure out how many magnesiums and chlorides that you would need by using the crisscross rule. So if magnesium has a valency of 2 plus, and you know how we figure that out, I can explain it quickly. If not,
Yeah, can you explain
yeah.
it?
So in your data sheet in chemistry, you have a
Mm-hmm.
periodic table, and you can figure out valency by looking at each of the groups. So group 1 has 1 plus as the valency. Group 2 has 2 plus as the valency. And then this whole middle region we don't really know.
Yep.
Group 3 has a 3 plus. Group 4 can have a 4 plus or 4 minus. And then
Mm-hmm.
once you get to group 5, you start to move the other way. Has a 3 minus valency. Then group 6 has a 2 minus. Group 7 has a 1 minus. And group 8 has a 0 valency. Have you
Yep.
seen it before?
Yes, I've heard of it before.
Okay. So then say you have that magnesium that we just had before. Can you tell me what the
Mhm.
valency of magnesium is?
Two,
2. And why is it 2?
because it's in the second column.
Yes, it's in group 2. And then
Mm-hmm.
say you had chloride. What's the valency of chloride?
One,
1 and 1 with what charge?
one minus.
1 minus, because it's in group
Mm, is it the one in the very end?
almost the very end. The one right before the very end is
Mm, is it seven?
group 7. You can see chlorines here. So then when you make magnesium bonded to chloride, to figure out what number of each of those you have, you apply the crisscross rule, where you swap their valencies.
Mm-hmm.
And so you would have magnesium with 1 of them and chloride with 2 of them once you've swapped the valencies around.
Um,
And that would mean your final compound you write as MgCl2 because you don't
yeah,
represent ones. Does that all make sense?
yes.
Okay, have a go at one yourself. Have
Mm-hmm.
a go at, let's make one up. Let's say you do potassium
Yep.
sulfide. Potassium sulfide. Try work out what that would be as a formula.
Um, is it K2S?
It is in fact K2S. Good. Well done. So that's crisscross rule.
Mm-hmm.
Jump back. Polyatomic ions. These will come up again later, but if you don't know them yet, they will become very important. Have you seen any of these before?
Yep.
Okay, cool. And lastly, diatomic molecules. So certain elements exist as molecules that have two of them joined together. And all of these elements that occur in this way, they either end in gen or in. So if it ends in gen, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, when they exist on their own, they exist as molecules. So H2 gas is the way that hydrogen exists. Okay.
Mm-hmm.
Final thing is general chemical equations. Have you balanced chemical equations before?
Yes.
Okay, good. Can you try take me through how you would balance this here with H2O2 making water?
Mm, you would put like a 2 in front of H2O
Mm-hmm.
and a 2 in front of H2.
Great. And are we balanced now?
Yes.
Good. We have four hydrogens, two oxygens, four hydrogens, two oxygens, and we're balanced. A few more difficult ones to balance here. I think you've got the basics. So have a go at this one here, a tougher one.
Okay. Do you put like a 5 in front of H2O?
Five in front of H2O. Yes, that looks promising.
And then I put a 4 in front of CO2.
That looks promising too.
But then on the right hand side, there's 13 oxygens and oh,
13 oxygens on the right, and there's only two on the left.
yeah.
And we can balance that. How are we going to balance it?
Mm, do we write like 6.5 in front of those two?
Exactly right. You can do 6.5, or you can do 13 on two, and that would allow you to balance this equation. A lot of teachers don't like the fractions though. So what you can do instead is once you get to this stage where you've balanced it with a fraction, you can just take all the numbers and double them all. And you go 2, 13, 8, and 10 instead to give everything in whole numbers.
Yep.
Great. Good job.
Mhm.
These equations you may have come across, we'll cover them again in module 3, so not essential to know, but very important equations to come. Okay, and that brings us to the start of module 1. Question is for this module, how do the properties of substances help us to classify and separate them? So you should know some basic properties about certain substances, and then you can use those properties to use separating techniques. And we'll come across those in a second. The first thing we'll introduce, and this may be already common knowledge to you, but we'll go over it again, are UPAC nomenclature. Essentially, the naming conventions are the way we name specific compounds, ionic and covalent, They each are named differently though. Firstly, let's define what an ionic compound is. What's an ionic compound to you?
Um, is that with a metal and non-metal?
Good. And in terms of the electrons, is it the sharing of electrons or is it the donation and acceptance of an electron?
Donation and acceptance.
Exactly. So an ionic compound is where you have a metal bonded to a non-metal and they are attracting each other because the metal donates an electron to the non-metal.
Mm-hmm.
And that gives it a positive charge, whilst it gives the non-metal a negative charge, and hence they attract each other. Because positive
Yeah,
attract negative, that's your electrostatic attraction. A very useful word. You want to write that one down. Electrostatic attraction.
yeah.
So for an ionic compound, you name it with the metal as the first word, followed by either a non-metal as the second word or a polyatomic ion as the second word. So if it's a non-metal, you replace the suffix with "ide" and it would become, for example, magnesium chloride. Metal, then non-metal with an "ide" at the end.
Yeah.
Yeah. So then what would be Li 2O? What's the name of this compound? Try name it.
Lithium oxide.
Perfect. Good. Ionic compounds with a polyatomic ion. So certain polyatomic ions have negative charges, and most of them do. This one, for example, is called nitrate. And so when you have a ionic compound with a metal and a polyatomic ion, you just name it as such. Sodium nitrate, as an example.
Yeah.
What about this one here? Let's do CaCO3. Do you recognize that polyatomic ion?
Is it carbonate?
It's carbonate. And so what would this be called?
Calcium carbonate?
Right. Very good. Moving on to covalent compounds. Covalent compound, how do you think of that? What would you define it as?
It's when a non-metal and non-metal are sharing their electrons.
Great. And so they have a shared pair of electrons. The way you name them is a little bit harder. So you have a non-metal. Non-metals all are in the top right corner. So all of these ones here are your non-metals.
Mm-hmm.
And when you're naming them, the non-metal that is furthest to the left on the periodic table will come first. And if they're in the same group, the one that is further down is the one that I believe is named. Yes, that is named first then. So as an example, say you had carbon bond to oxygen.
Mm-hmm.
What would you name first? The oxygen or the carbon? Is it oxygen, carbon, or carbon, then oxygen?
Is it carbon then oxygen?
Yeah, carbon, then oxygen. And say you had CO bonded together. We name this as carbon monoxide. And you'll notice that you only have that prefix of mono in front of the oxide. You only need mono as a prefix in front of the second element, not the first one. So you
Yep.
don't have monocarbon monoxide, it's just carbon monoxide. So then what's CO2? How do you name this?
Carbon dioxide.
Carbon dioxide. What about N2O4?
Mm,
You need a prefix for the nitrogen.
is it dinitrogen?
Yes, followed by
Tetroxide?
tetroxide. Great. think you've got it for the most part. So you just need to name based on the groups. Then if it's in the same group, you name based on what's got a high period number. So SO2 is a good example. The reason why S comes first is because S has a period number of 3, while oxygen has a period number of 2. And so you name the sulfur before the oxygen. But that's a rare case. Most of the time you're just separating by group.
Mm-hmm.
All right. Have a go at naming. Let's do one more covalent compound. Let's do this one here. What's that?
Is it phosphate trichloride?
Almost. Almost. Phosphate is actually the polyatomic ion PO4.
Mm-hmm.
This is phosphate, but we're not looking at phosphate here, unfortunately. P represents what instead? Look at the periodic table. Try find one on your end as well.
Mm. Or is it phosphorus trichloride?
There you go. Phosphorus trichloride. Great. So that's our naming done. Any questions there? As always, ask all your questions. Doesn't matter how small.
Mm. For the SF6, how
Yeah.
would you name that one?
What do you reckon?
Mm. Sulfur with, I don't know the prefix.
Prefixes are here. So 6,
A hexa?
hexa. So hexa, and what comes after?
Fluoride?
Right, that's it. Sulfur, hexafluoride. And then you'll notice for all of your ionic compounds, you don't need any suffixes. So, or any prefixes rather. So for example, if you had iron oxide, that's all it is. Iron, you might want to specify its valency. So if you ever seen Roman numerals in a bracket, that's just referring to the valency of a transition metal. Iron
Mm-hmm.
3 oxide. You don't need to say di-iron trioxide. You just say iron oxide.
Yeah.
Okay, cool. Mixtures and separating techniques. We have two types of mixtures, a homogeneous mixture and a heterogeneous mixture. So you should know what each of those would look like. A homogeneous mixture is one where you have everything completely evenly distributed throughout. So if you were to make a solution by putting salt in, NaCl, and the NaCl is the all dissolving, it would be completely evenly distributed throughout the solution, this NaCl. And that's a homogeneous mixture, where the two
Mm-hmm.
mixtures are completely evenly spread out. A heterogeneous mixture is something like a bowl of cereal, where you have your bowl, and imagine you put your cornflakes in at the bottom, whatever they might look like. So you have them
Yeah.
there. And then you pour your milk over, and let's say you only fill it up to like this level. You now have milk there. You can see it's not completely even. You've got some cornflakes sitting on top. Some aren't even in the milk. It's not completely evenly distributed, and that's a heterogeneous mixture, where the two substances are sort of not evenly distributed. Any
Yeah.
questions there?
No.
Okay. Adding two more definitions, you can have pure substances being elements, and you can have pure substances being compounds. When we say pure substance, that just means you only have one substance present, whether it's
Or
only the element or only the compound?
Mm-hmm.
Okay. We then have two types of matter, element versus compound. What's the difference in your mind before I get into it?
Um, does an element have only one type of atom, but a compound has two or more different types of atoms?
Yeah, correct. So your element, one type of atom only, and it's always going to be homogeneous because it's only
Mm-hmm.
one atom completely evenly distributed. And compounds, two or more elements, they have a fixed ratio. So when we say, for example, NaCl, and both of these would have like an imaginary number one next to them. It's one sodium for every chloride. That's what this formula tells us. One sodium for every chloride.
Mm-hmm.
Okay. So to compare the terms of mixture versus pure substance, one more time. A mixture is where you have two or more substances. A pure substance is where you have one type of substance, either a molecule or an atom.
Yeah.
Example of a mixture would be salt and sand. Example of a pure substance would be oxygen gas in a gas tank, for example. You can
Mm-hmm.
separate mixtures into multiple different pure substances, but you cannot separate a pure substance into more pure substances. You just have that pure substance. Um, Mixtures can be homogeneous or heterogeneous, and pure substances are only homogeneous. The mixture can have composition or ratio of parts, and a pure substance is fixed composition. And lastly, the properties of a mixture are a mix of the different things that make it up, whilst the properties of a pure substance are exactly the properties of what you have. So if it's oxygen, then the properties are based on exactly oxygen, not a mix of salt and sand.
Okay.
Questions there? Okay. All right. You then learn about physical properties. Physical property is a characteristic of a substance that can be observed or measured without changing the identity of the substance. And they describe the appearance, state, or composition of a material.
Mm-hmm.
So different physical properties could be, for example, density, melting point, boiling point, solubility, magnetism. All the properties would involve the compound or atom or whatever it is you have not changing in its composition. So when you boil water and you take water from liquid to gas, that is a physical property of water, the change in state, because the water molecule has it changed going from liquid to gas?
Mm-hmm.
Has it changed in composition?
Yes.
It's still a H2O as a liquid. The only difference is you now just have a H2O with more energy that can leave freely. So in
Mm-hmm.
composition, it hasn't actually changed. In composition, it hasn't changed, going from liquid to gas. That's what makes it a physical property. Does that make sense?
Yes.
Okay. A chemical property, and we'll talk about this more as we go on. A chemical property would be some sort of property that arises from a change in your composition. So you can say water has the chemical property of being able to be hydrolyzed into hydrogen gas and oxygen gas, for example. And you can see that by the end of this process, water is no longer a water molecule. It's a hydrogen molecule and oxygen molecule. That would be a chemical property as opposed to physical. Does that make sense?
Um, yes.
Okay. So when I say density, what does that make you think of? What makes a substance dense in your own words?
Mm, is it like how heavy it is?
Yes, but you can have something really like not dense and very heavy, but you just have a lot of it. So say you have a you have a pillow in one hand and you have a brick in the other.
Mm-hmm.
Which one is more dense?
The brick.
Brick. And even if the brick is a bit smaller, it might weigh more than that pillow, right?
Mm-hmm.
So when you think about density, it's two things. It's about the mass and it's about the volume that that mass takes up.
Okay.
Density is equal to mass divided by volume. So the higher the mass and the lower the volume, the higher the density. So think dense means lots of mass, little volume taken up.
Mm-hmm.
Okay. Melting point, boiling point, temperatures at which solids turn to liquid, liquids turn to gas, respectively. So do you know what the boiling points of water are? Boiling point, melting point?
Um, I know the boiling point is 100.
Nice. 100 degrees Celsius. Important we clarify the units. What about freezing point? Same as the melting point advice.
Ooh, I'm not sure.
Freezing point would be 0 degrees Celsius. Think about your freezer in your fridge. It's always
Mm-hmm.
at like -3 degrees Celsius to keep everything frozen. Okay.
Yep.
Solubility, the ability to turn a substance into a solvent. So think about that example of putting salt into a solution once again. And magnetism, the ability for substances, usually metals, to be attracted or repelled by magnetic fields.
Mm-hmm.
Okay. So then why do we care about all of these properties? Because we can separate substances based on them. Let's have a look at our first example. So sieving, if you ever used a kitchen sieve to separate flour and like the lumps in flour, you can apply the same thing to separate large particles and small particles using a sieve. So the property that you're using for each of these techniques you need to know. So the property we're using here is particles of different size. And if you put large and small particles into a sieve and you move the sieve around, you'll notice the small particles all move through and the large particles stay stuck in the sieve as they can't pass through the small holes. They're too big.
Mm-hmm.
Any questions there? Nothing too crazy?
Oh no.
Okay. Magnetic separation. We're using now the property of magnetism. So you can separate a substance that is magnetic with a substance that is not. For example, iron shavings will be attracted to a magnet while sand will not. And hence you can separate those.
Yep.
And lastly is dissolution on this first part of the list. These are just separating mixtures of solids. So say, for example, you have a mix of sodium chloride and you have sand, and you place them both into a beaker like this. You have your sand, and let's say sodium chloride is red in this case. It's white in reality.
Mm-hmm.
What will happen when you put water into this mix of solids?
Um, would the salt be dissolved with the water?
Exactly right. So you put some water in, and all of a sudden, all of that salt, I'll show you the equation too. You won't know it yet. NaCl solid turns into Na plus Cl minus, which refer to as aqueous ions. Have you
Mm-hmm.
ever heard of aqueous before?
Yeah, does that mean it's soluble only in water?
It's soluble. Doesn't necessarily have to be in water, but it just means it's dissolved if you say aqueous. And usually we're talking about dissolved in water. So 99% of the time what you said is correct, but sometimes you can actually dissolve in things that aren't water.
Mm-hmm.
Okay, so then if you have all of that salt in the water now, how can you separate the salt from the sand? We need now a new technique to separate a liquid from a solid. Can you think of any ways we can separate the liquid from the solid before I move on?
Um, is filtration one?
Very good. We've got salt solution and sand. So number one, you could pour this into a filter funnel with filter paper inside. Say you had it like this, filter paper. And you'll notice that the solution would pass through and you'll be left with the sand in the filter paper because it can't pass through the smaller holes.
Mm-hmm.
That's one way. The other way is really basic. We call it decanting, but it basically just means to pour off the liquid. Literally just pour it out. Nothing too crazy there. You take your beaker and you pour out the liquid that allows you to keep the solid at the bottom of your container.
Mm-hmm.
Filtration, you can do that too. And you're separating large insoluble solids from liquids. Because as we said, all of your solid will just stick in the filter paper and stay there. Okay. And lastly, sometimes solids don't really sit to the bottom as well if they're of somewhat similar density. And your blood, as an example, blood has lots of solids which sit within it, your red blood cells that make it red. So it's all mixed throughout.
Yep.
But you can separate the solids in blood by using a process called centrifuging. Have you ever seen a centrifuge before?
Oh no.
Okay, let's explain this one. Essentially, what you have is you have a spinning arm, and on that spinning arm, you place a test tube of whatever solid and liquid you're trying to separate. In this case, let's say it's blood. Blood is made of a few different things. It's made up of red blood cells. It's made up of plasma. And red blood cells are more dense compared to plasma.
Mm-hmm.
Then when you place this into your centrifuge and you start to spin it round and round and round and round and round, the heavier things will end up being cast to the bottom of your test tube, whilst the lighter things sit on top. So you can see here, we've formed red blood cells at the bottom, RBCs, and we have plasma sitting above it as it's less dense. Does that make sense?
Yeah.
Okay. Centrifuging. Let's go back to that salt solution. So we had a salt solution with NaCl in it, NaClAQ, and you now have sand at the bottom still. Actually, no, get rid of the sand. So now you just have the salt solution, but you want to separate the salt from the water.
Mm-hmm.
Another technique you can use is evaporation. So if you place your solution in an evaporating basin, heat it over a Bunsen burner, you'll be able to turn your H2O liquid into H2O gas. And eventually, you'll be left with an evaporating basin with a little bit of salt residue just left on the bottom, with no water in it. And you will have separated your water from your salt. Important to
Yeah.
know, when you boil, does any of the salt leave in the water that's evaporating?
Mm, no.
No, it doesn't. It doesn't. So think of it as, have you ever made like a reduced stock or like any of that in when you've been cooking before?
Oh, not really.
Really? Not too much of a cook?
Mm-hmm.
Let mum do the work. So when you are boiling down really concentrated foods, you'll be essentially removing water and leaving behind the concentrated flavors. And it's the same idea here. You're leaving behind concentrated salt in this case, just not as tasty.
Yeah.
Okay, last techniques are liquid mixtures. So you can use distillation or a separating funnel in order to separate liquids which either dissolve in each other. So distillation for alcohol and water, these dissolve in each other. And so you can't use a separating funnel for these. Distillation is separation by boiling point. So liquids are different boiling points.
Mhm.
Let's say that you're trying to separate ethanol from water. And ethanol has a boiling point of, um, let's say it's 30, no, let's say it's 50 degrees Celsius, and water has a boiling point of 100 degrees Celsius. Have you ever done a distillation before?
Oh, not really.
Okay, cool. So say you have these two substances inside of your round bottom flask,
Yep.
and you're essentially trying to heat to a temperature that is between 50 and 100. So say you want to heat to 60 degrees Celsius. Which of these substances will turn to a gas, and which one will remain as a liquid?
Mm,
These are their boiling points, by the way, on the right.
yeah.
Which out of ethanol and water will turn to a gas?
Would it be water
Would it be water if we're at 60 degrees Celsius?
on ethanol?
Be ethanol. So you have ethanol turning into gas, ethanol gas, which then passes through the system into what we call a condenser. The water that was in the beaker, that stays as liquid water. It's not hot enough to boil.
Mm-hmm.
So the ethanol gas goes into this condenser. The condenser passes cold water through it, which is say 20 degrees Celsius. And as the ethanol gas goes through, its heat is removed and it cools back down to now 40 degrees Celsius or lower, 30 degrees Celsius. And so what happens to the ethanol inside the condenser?
Mm, does it go inside the beaker?
It does. And what state is it? If it's
A
dropped,
liquid?
good, because it's dropped back below its boiling point. So now it's recondensed, now liquid again.
Mm-hmm.
And you've now collected a sample of liquid, whatever it is you were testing for, in this case, ethanol. And you've left behind in the beaker, or no, sorry, in the round bottom flask, all of your water. You now have pure H2O, and you now have pure ethanol from separating by boiling point.
Yeah.
Pretty cool. Okay. Separation funnel. This one's a bit easier as well. When you have two liquids that don't dissolve in each other and they have different density, you'll find that the more dense liquid sits on the bottom on its own, and the less dense liquid sits on the top. So if you've
Mm,
ever put water and oil together in a container, have you ever done that? Water and oil?
yeah.
Yeah. And you would see that you would make distinct layers. You would have your water on the bottom, and you kind of have a jiggly layer of oil on the top. Two
Mm-hmm.
separate layers, completely separate, because they don't dissolve in each other.
Yeah.
Put that into a separating funnel. The separating funnel has a narrow neck at the very bottom, allowing you to let out a very specific amount of the liquid, and you would be letting out the more dense liquid to be collected into a container of some sort. So the
Mm-hmm.
more dense stuff comes out. Eventually, you would have let out all of the less dense substance, and you'll be left with just, sorry, you would have let out all of the more dense substance and just be left with the less dense one. And the more dense substance would have been collected in whatever container you had. So say it's all collected out now, the more dense substance. You've now separated the less dense from the more dense substance, and that's the separating funnel. Any questions there on any of the techniques?
Um, oh wait, can you explain the separation funnel again?
Yes, 100%. Um, so essentially, you've got two liquids, one sitting on top of the other.
Mm-hmm.
This valve controls whether the liquids can leave the separating funnel. So if it's closed, nothing can leave. And once you open it, liquid starts to drip out from the bottom.
Yep.
And once you open it, the substance that is on the bottom is the one that is going to be let out since it's more dense and it's adjacent to that valve.
Mm-hmm.
So eventually the water level or the liquid level go down and then down and down until you've let out all of that more dense substance, which is what's shown in this second sort of diagram. That's the case
Mm-hmm.
where all of the more dense substance has been let out, and now the less dense substance is all that's left in the separating funnel.
Yep.
And that means you have two separate samples, less dense, more dense, and you've
Mm-hmm.
separated. Does that make sense?
Yeah.
Okay. Any other questions? Please clarify anything that doesn't make sense.
Mm, I still don't get the distillation diagram.
Okay, perfect. Let's explain it again. And this is exactly what you should be doing through these classes. As soon as you get stuck, don't understand, just say, and then I'll explain it again. Much rather do it that way. So starting in here, we said we had ethanol and water inside the round bottom flask.
Mm-hmm.
Why did we heat to 60 degrees Celsius?
To boil the ethanol,
To boil the ethanol, and why didn't we put it at like say 150 degrees Celsius?
it will boil both of them.
Good. And we want to keep one of them as liquid and boil the other. So that's the first step, choosing the temperature. So then once you have ethanol going up, the gas is going into a condenser. What does the condenser do?
Mm, does it change it to liquid?
Changes the liquid, and it's because you have a much colder source of water pumping in and out, and
Mm-hmm.
that's taking energy out of your gas, turning it back to liquid, allowing you to collect it in your beaker.
Yep.
Yeah? Okay. And once you have that, you've collected all the ethanol,
Mm-hmm.
you've left behind all your water, and now you have two separated liquids once again, separated by boiling point. Does that make sense?
Yep.
Okay, good. Any other questions?
Mm,
Scroll back through.
well, I don't get how evaporation works.
Okay, let's explain it one more time. So imagine you have your evaporating basin, which contains sodium chloride ions, all in solution.
Mm-hmm.
So it's water is H2O with Na plus and Cl minus dissolved in it.
Mm-hmm.
When you boil that water and you boil this solution using a Bunsen burner, what will happen is the water will start to turn to gas. H2O, H2O, all turns to gas. And that means your water level starts to drop. You start to get rid of water,
Mm-hmm.
which means your water level starts to drop and drops again and it drops again until all you're left with is these sodium and chloride ions, which will reform into NaCl solid. And ultimately, you would get left with a situation where you just have sodium chloride, NaCl, NaCl, NaCl as residue on the bottom of your basin. So the water you would lose. That's why evaporation is a bit more of a crude method. You just lose the water. But you've been able to separate the ions that were in that solution on their own by the end of it.
Yeah.
Cool. Any other questions on that one or the other two?
Why does NaCl turn into a solid?
Good question. It requires sort of mod 5 to explain this fully from next year. So don't worry about it too much. But I will say Na plus and Cl minus as aqueous ions, that's the way they exist in water as individual Na plus and Cl minus. But when they're in water, the reason why they can exist as these ions is because they interact with water in a strong enough interaction. It should be to this one. Let's say it goes to, yeah, to the oxygen. Okay. So the interaction between the ions and water allow them to exist as ions. But once you remove the water, what ends up happening is the ions that were interacting with water now have to sort of make up the energy that was lost for breaking these bonds. And the only way you can do it is by forming new bonds back with chloride. And hence you reform the solid that you began with. That's way beyond what we're at right now. So don't stress if that made no sense. But understand that when you evaporate, the ions in solution will reform back as the solid that they began as.
Yeah.
Okay. All right. As enrichment, we're going to talk a bit about fractional distillation too. So this is sort of a harder way to do distillation. And the property that we're going to be using is, once again, boiling point. Liquids with lower boiling point will boil and condensate at lower temperatures compared to liquids with high boiling point. That's what we've just seen with distillation. Except this is a method where you have lots of different temperatures at the exact same time. So what I want you to imagine is crude oil, first of all. This is what you get from the bottom of the ocean when you drill up oil, and you have a mix of all of these substances here. Lubricating oil, paraffin wax, asphalt, fuel oil, diesel, kerosene, petrol, butane, and propane. You have all of those different substances in crude oil, but you want to separate them so that you can use them each for their own purpose. Turns out they all have different boiling points. Fuel oil boils at 370 degrees Celsius, diesel at 300 degrees Celsius, kerosene at 200 degrees Celsius roughly, petrol at 150 degrees Celsius, and butane and propane at somewhere below 20 degrees Celsius. And then the bottom substances somewhere above 400 degrees Celsius. So we can use what we call fractional distillation to separate all of these substances by boiling point in the one go. Say that you heat to 400 degrees Celsius. How many of these substances are going to turn into gas? Well, it's all of these ones will turn into gas. Does that make sense?
Yeah.
Why do they turn into gas? Just justify it quickly in your own words.
Because they're below 400 degrees Celsius.
Yes, and what specifically is below 400 degrees Celsius? It's their what point?
Their boiling point.
Their boiling point. Good. These are all their BPs, boiling point. Okay, so all of those substances will rise up. Lubricating oil, paraffin wax, and asphalt, they have a boiling point above 400. So they kind of just don't change. They end up sitting down at the bottom, and you can separate those on their own through a different method. But the idea is you've left those behind. They're not going to boil up. Everything else will though. And they pass through these special trays. These trays allow gas to pass up through them, but they don't let liquid pass back down. So liquid ends up getting collected on the trays, but gas can continue to go up through them. Does that make sense?
Not really.
Okay. How should I describe it? Imagine it as a sort of like a mushroom in a way.
Mm-hmm.
And then you've got a tray here. So you can start by passing gas up into this cylinder, and the
Mm-hmm.
gas can pass up and through that hole at the very top, allowing the gas to pass upwards into the next chamber.
Yep.
But if the gas, for example, was to turn back into liquid and condense here, can you see that the liquid has no way to pass back down? Unless like you make enough liquid for it to get into that gap. But for the most part, the liquid's not going to be able to pass back down.
Mm-hmm.
Okay. So what's happening in this vessel? I want you to imagine this whole structure that I've got on the screen. Imagine like a massive column going 100 meters up into the air. Really,
Yep.
really tall column. And your heat source at the very bottom. So as you go
Mm-hmm.
further up in the column, what's going to happen to temperature as you get further from the heat source?
Um, is it gonna rise?
Would the temperature rise? Think about it as if you had imagine yourself on a cold winter day and you're standing next to a campfire. Is it really hot next to the campfire?
No. Oh,
I think
yes.
I think it'd be pretty hot next to the campfire. I
Mm.
wouldn't want to be too close, but really
Yeah.
hot campfire. You're standing about 2 meters away, very hot. Now, what if you walked 100 meters away from the campfire? Is it still as hot?
No.
No, the temperature is much lower. And this is the idea I want you to take here. You have a column at the very bottom with 400 degrees Celsius of heat. Imagine that as your campfire.
Mm-hmm.
If you're at the very bottom, it's very hot. The further you go up, though, what happens? You're getting further and further away. Temperature becomes
Um, lower?
lower. That's the idea. So the further from the heat source you are, the lower the temperature will be. Does that make sense?
Yep.
And that's what's happening. In this first chamber, the temperature is 370 degrees Celsius, enough to boil your fuel oil, but at some point, let's say up here, it becomes 350 degrees Celsius. So what's going to happen to the fuel oil as it passes into that colder region?
Mm, I'm not sure.
That's all right. We said the boiling point was 370 degrees Celsius. So what if the
Mm-hmm.
temperature dropped below 370 degrees Celsius to 350?
Mm, does that mean it got cooler?
Yes. And if you drop below boiling point, that's the same as saying you're dropping below the condensation point.
Mm-hmm.
And so you would turn from gas to
To liquid?
liquid. There you go. Your gas will turn into liquid and you'll start to collect liquid in your tray, which will run off and be collected in a separate container. You've now got fuel oil separated.
Mm-hmm.
That makes sense?
Wait, how does it turn into a liquid?
Yes. It turns into a liquid because you've dropped below the boiling point. So if you're above boiling point, say you have temperature 400, your substance will exist as a gas because it's above the boiling point.
Mm-hmm.
But as soon as you drop below boiling point, your substance will turn back into liquid. So you have 350 degrees Celsius, your substance will now exist as a liquid. So the understanding that we need is boiling point is not just talking about what temperature you turn into a gas, It's also talking about what temperature your gas turns back into a liquid, your condensation temperature as well. Does that
Mm-hmm.
make sense?
Yeah.
Okay. So let's continue up. We've removed fuel oil, but we've got a lot of other substances. So we continue up through to here at 300 degrees Celsius. And at the top of the container, say it's 280 degrees Celsius. How are we able to collect diesel, which has a boiling point of 300 degrees Celsius? How can we do that?
Mm, we lower the boiling point.
We can't change boiling point. We can change something else.
Mm, the temperature.
Temperature, good. As you go further up, as I've been saying, temperature gets lower and lower. At some point, it drops below 300. And so when the
Mhm.
temperature drops below 300, what's going to happen to diesel gas?
Turns into liquid.
It's a liquid. And so you can collect it, collect it, collect it, and remove it. And now you've got a separate sample of diesel. The rest of the
Mhm.
gases rise up. Kerosene has a boiling point of 200. How can you collect kerosene separately?
Um, when the temperature is at 180 degrees Celsius,
Good. Let's say it's 180. What will happen then?
you can then collect it into liquid.
Good. And that's now pure. And you can repeat one more time. Petrol, if it drops below 150, collect it, collect it, collect it, collect it. Separate sample of petrol. What happens to butane and propane? If they have a boiling point somewhere below 20, and the top of our container can't drop below 20 degrees Celsius because that's atmospheric temperature,
Hmm.
what will happen to those? Will they turn to
Um,
liquid or do they stay as gas?
they stay as gas.
Stay as gas, and we may potentially lose them to the atmosphere. Or if we have a system to collect it, great, we can collect them too.
Mm-hmm.
Fraction distillation. That's probably the hardest science concept you've ever come across. Pretty
Yeah.
complicated, but once you've gone through it, it's all very logical. Would you agree?
Mm-hmm.
So this is the whole thing with chemistry is the first time you see things, things will appear very challenging. But once you've gotten your head around it, chemistry is very applied. And you just take that concept you've learned in one place, and now you can drag and drop it and put it somewhere else, and you can apply it in all different places.
Mm-hmm.
So go into the subject with a very open mind, try your best to understand things for the first time, challenge yourself, and you'll
Mm-hmm.
find that the subject actually over time becomes a lot easier. It rewards you. It rewards you for doing the hard work early.
Yeah.
Okay, we've got a few mixtures here. I'm going to give you 5 minutes to try figure out what you would use as a separating technique for each of these mixtures. So I'll put 5 minutes up. Write down what technique you would use next to each one.
Mm-hmm.
And you can use the table that we had before. Give it a go.
Yeah.
How are we going?
Oh, good, I finished them.
Okay, great. Let's go through them. So what have you got for number one?
Saving.
Sieving, good. And justify why?
Um, I think when you sieve, are you left with the gravel?
The gravel would be sort of bigger particles, and the sand will be really fine little particles. So what's going to pass through and what stays in the sieve?
The sand passes through, but the gravel stays in the sieve.
Yeah, correct. Good. Number two, iron filings and solid sulfur.
Magnetic separation.
Yeah. Magnetic separation would be good. And which out of the two is magnetic?
The iron filings.
The iron. Good. Number three, sand and water.
Mm, Filtration.
Filtration, that's perfect. You could do it one other way. Can you think of the other one?
Mm, is it the filter funnel?
Filtration is the filter funnel.
Uh-huh.
One other way, you can do it too.
Sedimentation.
Sedimentation, and there's one other word.
Mm,
It means to pour out, just in a bit fancier terms. Sedimentation starts with D.
mm,
D
Cantation.
decantation. Yes. That'll be your two ways to do the mixture of sand and water.
Mm-hmm.
Have a suspension of blood containing plasma and solid red blood cells. What's this one?
Centrifuging.
Centrifuge. Salt dissolved in water.
Evaporation.
Evaporation. Mixture of ethanol and water.
Distillation.
Distillation. Ooh. Distillation. And lastly, mixture of vegetable oil and water.
The separation funnel.
Separating funnel. And you could use distillation for this too as well if you wanted to. But
Mm-hmm.
separating funnel is what we were looking for mostly. Great. So those are pretty much all your separating techniques. Okay. The final thing we'll talk on is we'll talk about mass calculations, being able to separate or calculate percentage composition by weight of component of elements or compounds, so you can figure out what percentage of a compound is a particular element. Your intro to chemistry maths. So percentage composition is the relative mass or proportion of each element in the compound. Percent of the component is the mass of component divided by the total mass. So let's do an example to show you what I mean. Say that you have a sample of an ore, which means just like a mix of metals. 10.63 grams is its weight, and it contains 1.55 grams of nickel and 0.76 grams of cobalt. Question asks, calculate the percentage composition of nickel and cobalt. So if you want to find the percentage of nickel, you take the mass of nickel that's in the sample, divide it by the total mass, and you would find that it's about 15% of the
Yep.
compound is made of nickel. Do you know what I mean by 2SF, significant figures?
Yes.
Yes. So how many significant figures would a number like 15 have, just to clarify?
2.
2. What about a number like 10.63?
Is it 4?
It is 4. And what about a number like 0.76?
2.
2. Good. And so the rule for chemistry and physics calculations, you only need to worry about physics. Sorry, I need to worry about chemistry. The
Mm-hmm.
rule is that the number of significant figures you leave your answer in is based on the smallest number of sig figs from the question. So from the question, we have 2, 4, and 3. Actually, it'd be correct here to leave it to 3 sig figs since you're taking 1.55. So it should be 15 point whatever percent it is to 3 sig figs instead of 2.
Okay.
Second question, percentage cobalt. Can you have a go trying to figure out what percentage of the compound is made up of cobalt?
Okay.
You might need a calculator.
Mm-hmm. Mm, 0.071.
0.071. That sounds good, but how would you leave it as a percentage?
7.15.
7.15. And then because for this mass, you used 0.76, which had 2 sig figs, you would then leave your answer to 2 significant figures. So what would your final answer be?
Um, 7.2.
7 point. Ooh, it's close. Because I had 7.1495. Which way would that round?
Mm, was it just 7?
It would, we're leaving 2 significant figures. So it's either 7.1 or 7.2. If we
Or
have 6.1495, what do we round to?
7.1.
7.1. So just being careful, don't round too early. Try
Mm-hmm.
reading your exact number.
Okay.
7.1% is cobalt. Great.
Mm-hmm.
Going the other way, sometimes you can get given a mass, 152 grams, for example, and you get asked to turn that into the composition using percentages. So you might have a 152 gram sample that contains iron and sulfate, and they tell you there's 37% iron, 21% sulfur. So you should be able to figure out what's the mass of iron, therefore, by doing, it should be 37. 152 times 37 divided by 100 is equal to 56 grams. Or for sulfur, 152 times 21 and 100 is equal to 32 grams. And you can figure out the mass of components using percentages going the other way.
Why do we multiply by 21?
Yep. So it's kind of 152. I would think of it more as times by 0.37, but they've represented it as 37 on 100 instead of 0.37 because
Mm-hmm.
that's from the percentage.
Yeah.
Yeah. And then finally, if you want to calculate the unspecified percentage of oxygen, because you know that the compound is all iron, sulfur, and oxygen, you can take the overall mass, subtract the mass of iron, and subtract the mass of sulfur to be left with 64 grams of oxygen as what's left over.
Mm-hmm.
That will make sense too. Okay, let's have a go at one practice question, and this will be the last thing we do today.
Mm-hmm.
Let's say that we have, which one do you think is harder, going from mass to percentages or going from percentages to mass?
Um, percentages to mass.
Okay, let's do that one then. Let's have a go at question 4. And just let me know when you're done.
Mm-hmm. So is the mass of nitrogen 30 grams?
The mass of nitrogen, let's check the answer. Yes, it is. And how many significant figures did you leave it to?
Mm, 2.
Justify why it's 2.
Um,
Which of these numbers is the smallest significant figures?
hydrogen.
Hydrogen, 8.00. This is actually 1, 2, 3 significant figures because trailing zeros are significant.
Oh, okay.
Yeah. And so
Mm-hmm.
what would 25.0 be? How many significant figures?
3,
3. And what about 120?
2.
This one's also 3.
Oh,
Because a trailing zero is still significant.
mm-hmm.
And so you should leave your answer there for 2, 3 significant figures. Try the other two.
Is the mass of oxygen 74.0?
Not quite, 74.0. You should be able to find the hydrogen mass first
Mm-hmm.
using this 8%. What did you get for that?
16.
16. I think that's a little bit big.
Mm.
What was your calculation to get there?
Um, do we have to do like the mass of the compound minus the nitrogen's mass minus the oxygen's mass to find the hydrogen's mass?
Yes, but you can't find oxygen mass without a percentage of it. So you'd have to find hydrogen first,
Mm-hmm.
mass, and that would be 0.08 times by 120 grams. Does that
Yeah.
make 8% of 120? And that actually gives you 9.6%. if you times by 100%.
Mm-hmm.
Sorry, 9.6 grams. And so now you have the mass of nitrogen and you have the mass of hydrogen, and now you apply that to find oxygen.
What was the mass of nitrogen?
I think you said it was 30.0.
Yeah.
So then what's the mass of oxygen?
80.4.
80.4. I think that's correct now. Check. There you go. 80.4, 9.6, 30.0.
Mm-hmm.
All right. And that brings us to the end of today. First content session done. We got 4 more content sessions to finish the whole module. Hopefully that wasn't too bad. Would you say on a scale of 1 to 5, how's your understanding? 5 being totally understood, 1 being very lost.
4.
Yeah, I think it's a good 4. It feels like a 4 from my end as well.
Mm-hmm.
So I'll leave it with you for this week. There is homework on the classroom, which we encourage you to attempt. We can't force you to do anything, but we
Mm-hmm.
do really encourage you have a go at the homework, and that way you can consolidate your learning. So that's all for today. Enjoy
Yep.
your weekend otherwise, and I'll see you back next week to go through the next session.
Yes.
Okay. See you, Aniga.
See you.
Bye.
Bye.